Okay, some more problems from section 9.5, and this is number 49, and this is a very interesting problem. So try to make sure you keep with it. I think you'll get a lot out of it. This is our series x plus pi to the n over the square root of n as n goes from the summation as n goes from 1 to infinity. So first of all, like we've done before, we're going to use the ratio test and check for absolute convergence. So we take the absolute value of this series. We're going to take the limit as n approaches infinity. Remember, we're using the ratio test, the limit. We're going to use the absolute value to check for absolute convergence. Because if it converges absolutely, it does converge. So the limit as n approaches infinity, and every time we see an n, we put an n plus 1 and divide it by this, so we'll just invert and multiply. Then we'll rewrite this as x plus pi to the n, the absolute value times x plus pi. And this stays the same, this stays the same, and this stays the same. And then we can cancel out this x plus pi to the n, and then we'll put the n's together. So we've got n, the square root of n, over n plus 1 times the absolute value of x plus pi. That's going to be 1. This limit will be 1. And if I take the limit, if we think of as n approaches infinity, this 1 becomes insignificant. So I got the square root of n over the square root of n. Okay? Which indeed will be 1. So this limit goes to 1, so we just have this. So this is equal to L. This series converges absolutely for L less than 1. So I set this absolute value less than 1. Okay, I hope everybody's with me and think about this. It all makes sense. Then I break it up. Minus 1, less than x plus pi, less than 1. Then I will subtract pi from all three parts. And this is our interval of absolute convergence. Okay? Now we want to check the endpoints, and these are our endpoints. So we know it converges absolutely on this interval, because those are all the values where this is less than 1, or L is less than 1. All right. So we check the left endpoint. X equals negative pi, negative 1. So what we do is we put this back in the original series. Here's the original series, just to review. Every time I see an x, I put that value in. And I put it in green so you can see there how it goes into the original series. So that's negative pi, negative 1, plus pi to the n all over the square root of n. But negative pi plus pi become 0, so I just have negative 1. And this is an alternating series. I wrote it to the exponent, but they're the same. So I looked over there. If I use my alternating series test, this is u sub n is 1 over n, the square root of n. It's greater than 0. It's decreasing for n greater than 1. And the limit is 0 as n approaches infinity. So therefore, this converges by the alternating series test. So therefore, it converges at that endpoint. So my interval of convergence will include that endpoint, so I'll be closed there. Now let's check the other endpoint, the right endpoint, x equals negative pi plus 1. And again, I put this in the original series, but I don't have the minus, I don't have the negative now, negative 1, so I just have 1 to the n, which is just 1, and then this series will diverge by the p-series test, because p equals 1/2, which is less than 1. It has to be greater than, or it has to be greater than 1. It's not even equal to 1, but greater than 1 to converge. So it diverges by the p-series test. So this is not on my interval convergence. So if I look at my interval convergence down here, closed at negative pi, negative 1, open at negative pi plus 1. That's the interval convergence. Now we also want to check for conditional convergence, because we want to see what's is it absolutely convergent also at this endpoint. We know it's not going to be absolutely convergent at the right endpoint because it diverges. And remember, absolute convergence implies convergence. And if you take the counterpositive of that statement, if it's not convergent, it's not absolutely convergent. So it can't be absolutely convergent. So we don't have to worry about this. So this right endpoint is out of play. So this is going to be okay. But we might have something here if it converges. Okay? And it can, and we've seen some where it converges at the left endpoint, even actually both endpoints. Absolutely. So we need to check that. So we're going to, and in reality, by checking this for absolute convergence, we're actually checking it for conditional convergence, because we know it converges if it doesn't converge absolutely, then it converges conditionally. All right? So we'll take the absolute value of this series. Go back up here. This is the one up here. Take the absolute value of that, and what does that do? Gets rid of the negative 1 just like this did in a way. So therefore what we have is, or it results in this. Okay? So the absolute value of the series is this. And again, this diverges. Same thing by the p-series test. So therefore it doesn't converge absolutely at this point. So that's why that would be open. Okay. I'm sorry, at this point. Pardon me, excuse me, wrong point. We already know it doesn't converge absolutely at this point because it diverges at that point. I'm looking at this point, pardon me. So therefore it doesn't converge absolutely at this point. So that's still open for absolute. Okay, so there's my interval of absolute convergence. But since it converges at that point, but not absolutely, it converges at this point, but not absolutely, converges but not absolutely, then that's a point of conditional convergence. Converges but not absolutely. Okay, converges but not absolutely. Therefore, x equals this point, negative pi negative 1, is a point or a value of conditional convergence. And I wrote down here again, so you remember that. Conditional convergence means it converges, but not absolutely. Okay, I hope that makes sense now. Okay, so think about that. Say it to yourself, write it down on a little card, whatever. Helps you remember that, and then you'll have that concept down. It's a tricky concept, so you have to spend a little bit of time on it. That's why we've done as many problems as we have. Okay? So remember that. Converges, but not absolutely, therefore conditionally. All right? Diverges here, so it doesn't converge absolutely. No problem. Okay? Hope that helps.